In this lecture, we will be solving a problem from regular languages and finite automata. And this question is from GATE 2013. So for our students who are not from India, GATE stands for Graduate Aptitude Test in Engineering, and it is an examination held in India that primarily tests the comprehensive understanding of various undergraduate subjects in engineering and science. So the questions that are from GATE are mostly good and standard questions, and by solving these questions you will also have a better knowledge and understanding of the subject and various topics from this subject. Alright, so let's try to solve this question. The question says, consider the DFA A given below. So we have a DFA given here, and there are a few statements given here, and we have to find out which of the following statements are false. So the first statement says the complement of LA is context free, and in second statement there is a regular expression given, and we have to find out whether this is true or not. That means whether this DFA can be expressed using this regular expression or not. And then the third statement says for the language accepted by A is the minimal DFA. And then the fourth statement says A accepts all strings over 01 of length at least 2. And we have a few options given here, options A, B, C, and D, where option A says statements 1 and 3 only are false, and B says 2 and 4 only are false, and C says only 2 and 3 are false, and D says only 3 and 4 are false. So in order to find out this, we need to see if statements 1, 2, 3, and 4 are either true or false. So in order to do that, let us analyze each statement carefully and let us see if we can find out whether the given statements are either true or false. Alright, so the first statement says complement of LA is context free. So if we look at this, this is a DFA. Now if it is a DFA, we know that it can be expressed using a regular language. Now if it is expressed using a regular language, we also know that the complement of every regular language is also a regular language. That is a thing that we already know. Now, if something is regular, we also know that that should also be context-free, but not vice versa. Every regular languages are context-free, but every context-free languages are not regular. So, since this is a regular language, this is also a context-free language. And the complement of every context-free language is also context-free. So, from all this, we can say that statement number 1 is true, because since this is regular, it is also context-free, and if it is context-free, the complement of every context-free languages are also context-free. So statement 1, which says complement of LA is context-free, is true. Alright, now let's go to the second statement. In the second statement, here we are given a regular expression, and it says that LA, that means this DFA can be expressed using this regular expression. So in order to find out whether this is true or not, we need to convert this DFA to its equivalent regular expression, and we need to see if it is same as this one. And in order to do this, we need to recall the lecture where we discussed the designing of regular expressions from DFA. And if you don't know how to do it, I will leave a link in the description to that lecture, and you can watch that in detail, and you can also see the examples that we have discussed. Alright, for now let us try to solve this and try to find out the regular expression for this DFA and see if it is going to be equal to this. Okay, so now I have copied down that DFA down here, and also the expression is here. Now we will see if we convert this DFA to its regular expression, will it be equivalent to this one. So in order to do that, let me give some names to these states. So let me call this state A, this will be B, and this will be state C. So as we see, A is the starting state and C is the final state, and B is another state that we have here. Now in order to convert a DFA to its equivalent regular expression, we have to make the expressions for each of the states that we have. So starting with the final state C. So C can be written as, how do we do this? We have to see which are the incoming transitions to state C and from which states are they coming. So we see that there is a transition coming from state A to state C with input 0. So we have to write A0 plus And from B again there is another transition coming to C with input 0, so I can write it as B0 plus, and from C itself there is a transition to C with inputs both 0 and 1, so we can write it as C0 plus C1. So this is my first equation. So in the same way, B can be written as A1 and B1, because from A there is a transition coming to B with input 1, and from B itself there is a transition with input 1. So I can write A1 plus B1. So this is my equation number 2. And then I have to write the same thing for state A. So in state A we see that there are no incoming transitions except this arrow which denotes the starting state. So we write it as epsilon. So the starting state or the starting transition is denoted using this epsilon. So this is equation number 3. Now we need to solve equations 1, 2 and 3 to find out if we can get this regular expression. Alright, so first of all, we see that A is equal to epsilon. So I can substitute the value of A into equation number 2, that means in B, and I can replace this A with epsilon. So if I do that, let's see what will we get. So equation number 2 can be written like this. So equation number 2 was initially B is equal to A1 plus B1. Now if I replace this A with epsilon, what I get is, instead of A I put epsilon, so epsilon into 1 plus B1. So this is what I get. Now epsilon into anything gives that same thing itself. Epsilon into R is R itself. That is the identities that we have. So epsilon into 1 can be written as 1 itself. So 1 plus B1. So this is what we have. So B is equal to 1 plus B1. Now if you look at this equation is of the form R equal to Q plus RP. So if we have an equation of this form where R equal to Q plus RP, by Arden's theorem we can write R equal to QP star. So this can be written as R equal to QP star. So this is by Arden's theorem, which we have already discussed. And if you don't know Arden's theorem, I will leave a link in the description where you can check it out. So this equation, how can we write it? So B is R, Q is 1 and P is 1. So if I write R equal to QP star, it will be of this form, B equal to 1 1 star. So this is how we can write B. So we have got B which is equal to 1 1 star. Alright, so A is equal to epsilon, B is equal to 1 1 star. Now we can replace this in equation number 1 to get the value of C. So let me write down equation number 1 here. So equation 1 was C equal to A0 plus B0 plus C0 plus C1. So this is equation number 1. And here I will replace A with epsilon and B with 1 1 star. So C is equal to epsilon into 0 plus, instead of B I'll be writing 1 1 star, 1 1 star, and this 0 comes down as it is, plus, and from here C0 plus C1 I can take out C common. So if I take out C common, we get 0 plus 1. Alright. Now we again know that epsilon into 0 is 0. So let me rewrite this equation like this. Epsilon into 0 is 0 itself plus 1 1 star 0 plus C 0 plus 1. So this is what we have. Now again, if you look at this equation is of the form R equal to Q plus RP. So again we can apply the same Arden's theorem and write R equal to QP star. So here what is my R? R is C, and what is Q? Q is this whole thing, 0 plus 1 1 star 0, and then P star. So what is P? P is 0 plus 1. 0 plus 1 star, because it is QP star. So this is what we get. Now I can write this like this. Let me just write this 1 1 star in the beginning, 1 1 star 0, and this 0 comes here. So I'm just rewriting it, just rearranging it. Then 0 plus 1 star. Okay, so this is the regular expression that we are getting for this final state C. Now if you compare it with the regular expression that was given in our statement, it looks the same. 1 1 star 0, 1 1 star 0 plus 0 into 0 plus 1 star into 0 plus 1 star, and then here you have 0 star 1 star. So if you have 0 plus 1 star, whatever you multiply with this, it is going to be the same. So this thing and this thing, it is equivalent. So we see that this DFA can be expressed using this regular expression. So we see that statement number 2 is true. So statement number 1, we already found out that it was true. Now we saw that 2 is also true. So both 1 and 2 are true. Now the third statement says, for the language accepted by A is the minimal DFA. That means that this statement is telling us that this is the minimal DFA. That means even if you try to minimize this DFA, you won't get anything more minimized than this. This will be the maximum minimized DFA. That means this DFA will have 3 states and not less than 3 states. So in order to find out whether this is true or not, we need to try minimizing this DFA. And in order to do that, we have to recall our lecture where we studied minimization of DFA. And again, if you don't know it or if you have not watched it, I will leave a link in the description where you can see it in detail. Alright, now let's try to minimize this DFA. Alright, so here I have copied down the DFA again. Now let me give names to these states again. I'll call it A, B and C. Now in order to minimize this, what we have to do is, we have to do the 0 equivalence, 1 equivalence and so on. So if you don't know how to do that, please watch the video. Links are there in the description. So in order to find 0 equivalence of these states, what we have to do, first of all, we have to find the 0 equivalence. So for 0 equivalence, we have to make 2 sets, and in the first set, I will put all the non-final states, and in the second set, I will put all the final states. So I'll make a set here, and what are my non-final states? A and B. So A and B will be in this set, and the final states, it's only C. So C will be in a separate set. Now for 1 equivalence, what we have to do is, we have to use this row of 0 equivalence, and we have to check that if they are 0 equivalent to each other, then look at these 2 states and then see where they are going on getting inputs 0 and 1. And on getting these inputs 0 and 1, if they are going to states which belong to the same set, then we can say that they are 1 equivalent. Let's see how to do that. So here we see that A and B are in one single set. So we have to see where does A and B go on getting inputs 0 and 1. So first let's check for input 0. Where does A go on getting input 0 and where does B go on getting input 0? A on input 0 goes to C, B on input 0 also goes to C. So they are going to the same state. So that is fine. Now let us see where do they go on getting input 1. A on input 1 goes to B, B on input 1 also goes to B. That means they are again going to the same state, which is B. So we saw that on both input 0s and 1s, they are going to the same states. So we can say that A and B are 1 equivalent to each other. So since they are 1 equivalent to each other, we can put them in the same set again. And you don't have to check anything for C because C is separate and alone by itself in another set. Now we see that the row of 0 equivalence and 1 equivalence is the same. Here we have AB in one set and then C. Here also we have AB in one set and then C. So if you find that in both the rows there is no change, so even if you continue for 2 equivalents, 3 equivalents and so on, there will be no change. So this is the final thing that we can get. And from this what we understand is that A and B can be combined into a single state and C will be another state. So our DFA can be redrawn as follows. So A and B will now be a single state and then C will be another state, and since C was the final state, here also C will be the final state. And here since A was the initial state, here AB will be the initial state because A is over here. Now let's see where does AB go on getting input 0 and 1. So we see that on getting input 0, both A and B they are going to C. That means AB will go to C on getting input 0. And on input 1, where do they go? Both A and B are going to B itself on getting input 1. So on getting input 1, both of them goes to B itself. And B is here, so we send it to themselves. And then C will be the same on both input 0 and 1, they will go to C itself. So we see that this is the minimized DFA. When we applied the technique of minimization, we were able to minimize this DFA into 2 states. Initially they were having 3 states, but we were able to minimize it further and we were able to design it using just 2 states. So what was our statement? So our statement said that for the language accepted by A is the minimal DFA. So the statement said that this is the minimal DFA. But just now we proved that that is not the minimal DFA, but the minimal DFA can be designed using just 2 states. So this statement number 3, which says that this is the minimal DFA, is actually false. This is false because we have shown that the minimized DFA has only 2 states and this is not the minimized or the minimal DFA. Alright, so statement 3 is false. Now let's come to statement number 4. Statement number 4 says A accepts all strings over 0, 1 of length at least 2. So it says that this DFA accepts strings over 0, 1 of length at least 2. So at least 2 means minimum the length should be 2. That means it will not accept strings which are less than 2. Alright. So the length of the strings accepted by this DFA should be at least 2. So if it is less than 2, it will not be accepted. That is what it says. So let us check from this DFA if this is true or not. So here we see that in this state, the starting state, if we get input 0, it goes to the final state over here. See, if it gets input 0, it goes to this final state over here. So if we get an input 0, it is accepted. So the statement says that it has to be at least of length 2, but here we found that even strings of length 1 is accepted. So this statement number 4 is also false. Alright, so we have found that statement 1 is true, 2 is true, 3 is false and 4 is false. So which will be the correct option from here? Here the options A, B, C and D are there, and then there is an option which says 1 and 3 are false only 2 and 4 are false, only 2 and 3 are false, and only 3 and 4 are false. So from this we found out that only 3 and 4 are the ones which are false. So the correct option for this question is option number D, which says only 3 and 4 are the statements which are false. So that is how we can solve this problem. So even though it is just a simple true or false problem, by solving this problem you are able to apply so many topics that we have discussed in regular languages and finite automata. So we were able to apply the concept of regular languages and context-free languages. We were able to apply the concept of conversion or designing of a regular expression for DFA using this statement number 2. And from statement number 3, we were able to revise the concept of minimization of DFA again. Alright, so many topics were discussed in this single question. So I hope this was clear to you. Thank you for watching and see you in the next one.